Let's get our attention into the last type of reactor that we're going to be discussing in this class. Packed bed reactors are one of the kind of tubular reactor or flow reactors. The main characteristics of this type of reactor is that it occurs under heterogeneous phase system. It involves fluid-solid heterogeneous reactions. Also, a reaction takes place on the surface of the catalyst. So you can imagine that the mass of the given catalyst now is an important factor instead of the volume as the other flow reactors. So let's see the different mole balance and assumptions and important factors, and then we're going to discuss a little bit of some of the reactors and conclusions on all the mole balances to proceed to the next part of the class. So when you talk about a packed bed reactor, catalysts are important, as I mentioned. We can predict, right, that increasing the mass of the catalyst, we can increase the performance, right, of the reaction or the conversion, because the reactants will be interacting with more catalysts in the reactor. We call mass of the catalyst, or we label it as W. That's going to be one of the design parameters that we're going to be looking at when we talk about PBRs. The other way that we can talk about a catalyst is that we can also increase the reactive surface area per gram per mass of catalyst, or we can also increase the active side of the surface per mass of the catalyst. These are important considerations if you're thinking in the future to do research on catalysis. A lot of the nanotechnology innovations concerning catalysts involve increasing the surface area or increasing the number of active sites. There's a lot of research on trying to understand these mechanisms and characterize these materials, and I recommend you to look for it, and there's a couple of professors here on campus that actually work with that. So we can define the rate of reaction for an heterogeneous system as the mole of A reacting times over the time times the mass of the catalyst. We can also see right here that we can get the regular rate by just multiplying the heterogeneous rate by the bulk density of the catalyst. Okay, if you notice in this definition, we can see that the reactor volume that contains the catalyst is of secondary significance. So now we're going to spend some time trying to derive an expression that help us to identify the mass of the catalyst for a PBR reactor. I want to show you figure 113 from your book. This is an schematic of an industrial catalyst reactor with vertical tubes packed with solid catalyst. So there's a couple of things that you have to notice. The feed gas is coming from the bottom in this particular schematic, and the products are being produced right on the top of the reactor. That means that the catalyst tube, which is represented by this gray tube going in this direction, the reactant is passing through these tubes, and then the products are being produced at the end. Make sure that you remember always that we try to make these models ideal, which means that as engineers, we have to spend a lot of time to make sure that we control temperature. Remember that we're working on isothermal reactors. We try to improve the way the coolant in this case is actually going through the reactors, and in this particular schematic you can see the coolant side baffles, which just go around, right, and go through all the reactor to try to control temperature. Remember, there are always temperature gradients, and we're going to see at the end of the course examples when heat transfer is an important parameter for the reactor design. If we remember for the other type of flow reactors, we worked or developed a mole balance in solve for the reactor volume or the volume where the reaction is happening. However, for a PBR, we will focus on the mass of the catalyst. However, the math behind it, the analytical solution, looks very similar, the model of the ideal PBR. So let's consider the following reactor. We have, in this case, let me change color here, the flow of reactant A, right, entering the reactor, okay, which is going to be the initial molar flow of reactant A, and then at the end of the reactor we have whatever is left, right, unreacted of reactant A. So in difference, compared to the other model, instead of having a differential element that is in terms of volume, now we're more concerned about the mass of the catalyst that is in this mass differential element. So if we look at it, we have to make sure that before we start doing the mole balance, we go back again to the assumptions. Remember, in this case, we have a isothermal reactor. We have isothermal reactor, okay? We also assume no radial gradients, okay, in concentration, temperature, or reaction rate. Once we do that, we can start doing the mass balance or mole balance in this case in this differential element. We have the flow entering to that element, the differential element, is FAW, right, minus the FA exiting, right, that differential element, okay, plus the generation of RA, of reactant A, delta W equals, or species A equals to 0. We are assuming no accumulation. Okay. Here we divide by delta W. We rearrange, and then we take the limit where delta W tends to 0, and we end up having an expression, right, the differential form of the above expression, and arranging that to have an expression for the heterogeneous rate of reaction. Another big assumptions for the ideal gas model for PBRs is that we are assuming that the pressure drop, there's no pressure drop, okay? And the other thing that we are assuming is that the catalyst, no catalyst deactivation. Okay, I want to make sure that you realize that in this class we will see deviations of the ideal model where we will have delta P equals to something. There's going to be a pressure drop over the differential element here, and the catalyst will deactivate eventually. So one of the important aspects of a chemical engineer is to actually predict this deactivation, or maybe select a catalyst that lasts long enough to have as much delta P equals to 0, right, there's no clogging or falling of the catalyst, and also that the rate is not changing, right, because the spaces or the surface area allowed for the reaction are being clogged throughout time. concluding with this analysis, we get that the W, right, which is the mass of the catalyst in the reactor, equals to the equals to okay. So this can be considered to be the mole balance or the design equation in terms of moles for the ideal PBR. Okay, remember the assumptions and the conditions for these reactors are important. An important aspect for the PBR also is that there is no pressure drop and there is no catalyst deactivation. Okay, this equation tells us, right, give us information about what is the catalyst weight necessary to reduce the entering molar flow down to a flow rate of FA. Okay, now I'm going to show you a little bit of all the mole balances, and then we're going to move on and start creating similar equations, design equations, but now with the conversion term. So as to conclude, right, the mole balance, here you have the generalized forms for the 4 common reactors that we cover, and we're gonna use or start using this and express all of these equations in terms of conversion, and we're gonna dedicate the rest of the videos on doing this. Once again, we have the mole balance in the differential form, and we typically try to define by the flow in terms of moles or concentration. It depends on what we're doing, and then we try to express the rate of reaction, and we learn how to get that from mechanisms. We can it can be given to you. You can infer that from the statement, maybe the units of K. There's always a way to get information about R, the rate of reaction. The other thing is that you have to typically focus on the limiting reactant, and we're going to see that in the next couple of videos and topics. Again, there's the only reaction, or the only reactor actually has an algebraic form is the CSTR. So we don't need to use integration factors or solutions depending on the order of the reaction. Pretty much we can use this straightforward. And then depending on the type of reaction, we are gonna get the integral form, right? That will be based on what is the criteria for that particular reactor. One important aspect that we're gonna see in the next videos and the classes is that we will try to combine different ways of combine different reactors to try to get the highest conversion, and we're gonna spend a lot of time on that because we want to design not only one reactor but actually a process, a couple of reactors maybe, right, that can improve the overall conversion of the species A, that based on that we can get how much we're getting out the product. Remember that we can always relate one species with the other in a chemical reaction. So this is the final video. Stay tuned for the rest of the videos for this part.